Hello and welcome to lesson number 6, Implicit Differentiation, implicit. What we've been doing to this point has been explicit differentiation, where I have had an x value input of some f function, and I've been explicitly evaluating the differential of f in terms of x. Sometimes, though, I can't necessarily do an explicit form, and I have to do what's called implicit differentiation, where I have to determine what another function is in terms of that x that may not be explicitly written as a function of x. Now that's a mouthful of gibberish, but when we watch it happen, it won't be so hard to understand. I'm going to pull a few example problems out of the book, because if I just make them up in my head, I could end up in a circular thing. I don't want to do that. So I'm going to pull some direct examples from our book, and our book is the Larson Calculus of a Single Variable 10th edition that we're using in our AP courses this year, which is 2015. So, without any further ado, let's take a look. So, we are going to differentiate, or take the derivative of, this expression. Find dy dx, so that's what they're asking me to do. What we've been doing all along, find dy dx of. Now, up to this point, we've been writing like 2x squared minus 3, or the natural log of x, or e to the 2x plus 5. We've been writing a pretty much an explicit, or a set of explicit functions. Now, I'm going to write it this way. Y cubed plus y squared minus y5, or 5y, I'm sorry, y cubed plus y squared minus 5y, that's not all of it, minus x squared equals negative 4. Okay, so just look at that for a moment and ponder how you might do that. All right, welcome back. Now, this is not so easy as to just solve for y. Sometimes I could just solve for y, and if I can get it into y equals whatever, I can use explicit differentiation. Maybe in the next example I'll show you one that works both ways. But this one I can't just solve for y easily. So what I'm going to do is I'm going to say, look, it says to do dy dx, so I'm going to do dy dx of this side and dy dx of this side. What I do to one side, I do to the other. That basic rule of equality that we apply in algebra. So this is still y cubed plus y squared minus 5y minus x squared, and this is negative 4. Okay? Now, y is not an x, all right? And since y is not an x, we're going to have to use the implicit method, where we're going to assume y is a function of x, but we don't know the function, okay? So we can take the y as a function of x by using the composite function strategy, or the chain rule. So I can take the derivative of this function. So the derivative of this, the outside of it, is something to the third power. That's straight up understandable. So I can say, well, that's 3 times something to the second power, right? And what's the inside? Well, the inside in this case is the y, that function that we were calling g earlier. And we knew that g was a function of x, and we're assuming that y is a function of x. So I don't know what the derivative of y with respect to x is, but I can represent it with this term dy dx. So if you think about it, it looks like you did the derivative and distributed that through. It's kind of the look that you get. All right? But you're really not distributing. You're doing the derivative of the sum is equal to the sum of the derivatives. Okay? That's what you're doing. Still those limits laws, basically. But when you went to do the derivative of the inside, you didn't know what y was, so you just wrote dy dx. If I knew what y was, I could figure that out. So this represents the derivative of the inside. Has to be there, otherwise I haven't done the chain rule. I hope that makes sense. Now let's look at the next one. I'm going to change colors as I go. The next one is y squared. So that's going to be 2y to the 1, right? dy, because that's still my inside, right? dy dx. You don't see that dy dx behind your stuff? You're not doing implicit differentiation. You're doing something that's neither real differentiation or explicit or implicit. Some blend in the middle that's nothing. So be careful. Let's change colors again. This is minus 5y. So y to the 1, right? When I do 1 times 5 is 5, y to the 0, so that's gone. That's 5y to the 0, or 5 times 1. But I still need the derivative of what y was before it disappeared, right? And so that is dy dx, right? Fair enough. So far so good, yes? It's not that hard. You just have to think through it. Now I'm going to do the derivative of this. But this is an x, you see it? So with respect to x, there's an x there. I couldn't do with respect to x because y was there, so I had to do the y and then the y with respect to x as a tail. But now it's there, right? So I can straight up do that. That's negative 2x to the 1, right? Now let me show you what you've always been doing, but we've never been doing it. Then I do the derivative of that thing inside. So I can think of that as the outside, and then x is the inside, right? So dx is the tail that would have, but dx is something over itself, right? And so we don't show it. So when I'm doing an explicit derivative, basically there's always that dx behind it, but I don't need to show that because it's just 1. We ignored it completely to this point, but now it is worth remarking about because it's the difference between the derivative of this y with respect to x. I took the derivative of x with respect to x, didn't I? Okay? And really, honestly, if I want to write this correctly, I probably should write this not dy dx, right? Because I'm not doing dy dx, I'm doing the derivative with respect to x. So let's make sure that our notations make sense. And it made sense as I was going till I got to here. So the derivative of this is that with dy dx. The derivative of this is that with dy dx. The derivative of this is that with dy dx. But the derivative of this is that with dx dx. Can you see how that works now? And so the derivative of this is going to be, well, imagine what's behind there, right? Remember? X to the 0. That's still back there, right? And when I do 0 times negative 4, I get 0x to the negative 1. So that's 0. It's still dx dx because I'm still doing dx dx, right? So that's still there. But 0 times 1 is, of course, 0. So I don't see it. Point taken, I hope. That you can see now why the dy dx appears here, but nothing appears when it's just x, because the dx dx is something over itself and cancels away. Okay? So now we can work this out. So let's continue. I'm going to extend the page a bit so we can see that a little bit higher. I don't have to bend down and write. So look, if you look at this, I notice that there's a dy dx in this term. There's a dy dx in this term. There's a dy dx in this term. There's no dy dx here and no dy dx there. So if I wanted to have all my terms have a common thing I could factor out, I would want to move everything that doesn't have a dy dx in it over to the other side. And that's what I'm going to do. I'm going to add 5 to here. Oh, I'm sorry. That's the wrong one. I'm not going to do that. I'm going to add 2x to here and add 2x to there, right? And now that's gone. And all the terms left on this side have dy dx in them, yes? And of course, this is going to be 0 plus 2x. So even though I don't need to, right, I'm going to rewrite this. But this time, I'm going to just rewrite the leftover pieces. So I'm going to rewrite 3y squared. That's there. I'm going to rewrite plus 2y. That's still there. I'm going to rewrite minus 5. That's still there. So I'm going to put them all in parentheses, and then I'm going to multiply them by the common dy dx. So I undistributed dy dx out. That's really all I did. So instead of writing it in 2 lines, I'm going to do it in 1. Undistributed dy dx out, and when I did that, it divided itself off of everything and left only what was its coefficient inside. Okay? And what was on the other side is 2x. I don't need dx dx anymore. I don't need that. I never did. I just wrote that so you could see that I wasn't doing something unique here that I hadn't always been doing. Okay? But the beauty of this, now I can solve for dy dx. It said find dy dx, right? So now I can find dy dx if the board will cooperate. I can find dy dx when I divide both sides by this. So I'm going to divide both sides by 3y squared plus 2y minus 5. Okay? Which of course means this is now just a giant 1. I did that on purpose so that it could go away. And I have dy dx equals 2x over 3y squared plus 2y minus 5. Now I could find the derivative for that function anywhere as long as I know a single point. So in other words, if I know an x value and I plug it in and get out a y, my x value would go in where it says x, and the output for that particular x value would go into the y spot, making y a function of x. Now everything is a function of x, and I could get a discrete value at any place. This is a derivative formula that lets me find the derivative anywhere on that function, as long as I know whatever input and respective output that point, input point dictates. That's what I would use. Okay? So that makes us have a way to find derivatives of really hard to work functions. And it begins to send us in the direction of what we'll be looking at later after all the calculuses at differential equations, where we have these kinds of statements where the variables are mixed and I can't just solve everything for y easily. And I got to work with it in its form. Okay? So let's look at another one. Again, I want to get them out of the book, so give me a second. So here's one. Find dy dx, or take the derivative with respect to x of x squared plus y squared equals 0. And so how I write that, in actuality, that's really not a good way to write it, but it's short and sweet for us. But what that really means is I take the derivative of the left side and the derivative of the right side. Well, when I do this derivative, oh, by the way, what is this shape? You should know that. And if you don't remember, if I have a power greater than 1, what did that do to my line? It made it what? Right? It made it curve. But what happens when I have a power greater than 1? It curves. So if I curve in my x direction, I get that parabola shape, right? But when I curve in the y direction, it curves it again, and it curves it into itself, and I get either a circle or an ellipse, depending on how it's stretched or squeezed. So when I've got x squared plus y squared equals a constant, I have a circle. X plus x minus h, y minus k, and that's r squared. That's from the conic sections. You should remember that. So the center of the circle is 0, 0, and its radius is 0. So it's a point. Does that make sense? I mean, it's almost not a circle at all, is it? It's a point. But could that have been another constant? Absolutely. I could have picked something that wasn't 0. It could have said 7. What's the derivative of 7? 0. I'd still be able to, it'd still kind of give me the same thing, except now that wouldn't just be a point. It would be a circle with a radius to square root of 7. So from a point and any concentric circle from that point, this is kind of the same strategy. It really isn't changing anything. So I just said that because you should think about, what is that shape? You should be thinking about that when you see a function. Could I figure out what that shape is? That's a good mental exercise. All right, so let's do this. Remember, the derivative of the sum is equal to the sum of the derivatives. So the derivative of x squared is 2x to the 1. And that's dx, so I don't need a tail. However, plus the derivative of y squared is 2y to the 1 times the derivative of the inside, dy dx. Since that's not something over itself, I need dy dx. I need that tail on the back. And then what's the derivative of this constant? 0. Because a constant has x to the 0 behind it. So that's 0, x to the 0, dx dx, so that's 0 times 1. So the 0's there. All the mental gymnastics to verify that are doable, but when you remember the derivative of a constant is 0, it makes your life easier. But you can always remind yourself why. Well, now I see I've got a dy dx here, but not here, so let's move it over, right? And I am left with 2y dy dx equals negative 2x, yes? And then I'm going to divide by the coefficient of dy dx because I want to have just one dy dx equals whatever. Notice the 2's cancel, so I can say dy dx equals negative x over y. And now I can find the tangent on that circle at any point on its circumference. But since it's a point, there won't be anything. But if that was a 16, then it would be at 0, 0 with a radius of 4, and I could find, because that would still be the same, right? Because that 16's derivative went to 0. So that's going to be actually the derivative for any circle at 0, 0 at least. Okay? Now, I don't know if you've noticed this yet, but when you're writing this, it can get kind of long, and I think you should write them all out. But after you've done the first set of homework, you can see that, you know what, once I factor this out, once I move this over, whatever I'm going to factor out ends up on bottom, right? So literally, if you think about it, if I come back to this other one, I could have said, look, let's see this pattern unfold here. I said, look, once I factor everything out, right, I could have basically written the 2x over here, and then everything I was going to factor out underneath of it. You see it? So it's really kind of quick algorithmically after a while once you see how it works, but I want you to do it with the steps. Okay? Want you to do it with the steps. So here's another one. Find the derivative with respect to x of, because couldn't I find the derivative with respect to y? Absolutely. We're just doing respect to x because it's calculus of a single variable right now. So the derivative with respect to x of x squared plus 4y squared equals 4. So it looks like it would be a circle, but these aren't the same. So that means this is multiplied by 4, right? Makes it go quicker, right? But since I'm curving in the y direction, it's going quicker. So I should have, I think, a flat and skinny ellipse, but I have an ellipse at least. It's not a circle. So that's not really in a radius anymore. I'd have to divide all of them by 4 to have, you know what I'm saying, where I have my a and my b and it'd be equal to 1 for it to be in its proper conic form. But look, it looks like a circle, but I don't have the same thing in its general form. I know it's an ellipse. All right, that's what I know. So let's go ahead and find the derivative. Well, again, I want to do the derivative with respect to x to all of it, which means both sides. So the derivative of x squared is 2x dx dx. Therefore, that's done. Plus 4, that constant, as we know now, for all the derivatives, can be pulled right out in front and ignored, and then do the derivative behind it. So the derivative of y squared is 2y to the 1, right? And then derivative of y with respect to x is dy dx. And the derivative of any constant, that's x to the 0, so that's 0 dx dx, or 0. Which one has a dy dx in it? This one does, and this one does not. So, what am I going to have? I'm going to have in the end dy dx equals this thing I moved over divided by this thing I'm going to divide off of both sides, which is 8y, which simplifies down to 1/4, right? So it's negative x over 4y. Okay? So it's really not hard. I mean, implicit differentiation is not that hard. It's just something that you got to use and fiddle with until you get the dy dx part. Okay? Now, I am going to talk a little bit about, let's say, one with a trig function, because I think you should have been doing them by now. So the derivative of, let me pull one out of the book again. I don't want to just pull that out of my own mind. Sine of y equals x. Okay. So let's say I have the sine of y equals x. I've had the sine of x equals y. That's a normal explicit derivative, right? dy dx equal negative or equal to cosine of x. But that's not what I have. I have the function of a function because y is a function of x. So I've got to do the composite, right? It's a composite function. I've got to do the what? The chain rule, right? So the outside is sine, the inside is y. So I got to be careful when I do that. This is a chain rule. So the derivative of sine is cosine with respect to the inside times the derivative of the inside, the derivative of y is 1y to the 0, or 1 dy dx. So that's 1 dy dx, I just don't see the 1. And the derivative of x with respect to x is 1. dx dx I don't show. Pretty straightforward, right? What's dy dx? Well, clearly, if I divide by the cosine of y on both sides, I have dy dx equals 1 over cosine of y. The reciprocal of the cosine, you're pretty savvy. I know you had me for trig, Carnahan, and those of you who didn't, well, you're still pretty savvy. What is cosine upside down as an equivalency? We have 6 trig function names, and 3 of them are the reciprocals of another 3. And if you remember, the first becomes last, sine becomes cosecant, cosine becomes secant, and tangent becomes cotangent. So I would really say a better answer would be what this is in its equivalent form, and that's the secant of y. Because that's what 1 over cosine is. It's the secant. All right? This is right, but this is better. Relatively, because it's one thing, it's easier to read. Okay? Let's look for another. Ooh. Here's one. Here's a fun one. Let's look at this one. We haven't done much in the way of this at all. And again, those special functions, you would see radicals. So let's do the cosine of y equals the square root of, the square root, we'll talk about that, 1 minus sine squared y. Well, I should be jumping for joy by seeing that expression from my trig class, but if you're not, that's unfortunate. You need to look at those trig identities, and there's some fundamental ones you want to know. The quotient identities, sine theta over cosine theta equals tangent theta. And if that's true, then the reciprocal of that, cosine theta over sine theta equals the reciprocal of tangent, cotangent theta, right? Those reciprocal thetas, sine is cosecant, cosine is secant, tangent is cotangent when I flip them upside down. I also would like to know the Pythagorean ones. Sine squared theta plus cosine squared theta equals 1, and the other 2 derivatives that you get from dividing everything by sine, you get a different derivative. When you divide that original statement by cosine, you get a different derivative. And those are your 3 forms. But look, sine squared theta. So let's write it over here. Sine squared theta plus cosine squared theta equals 1. All right? Why did I do that? Excuse me, I got a hangnail. Why did I do that? I did that because I see a 1 and I see a sign and I see a minus. And sure enough, I could rearrange this. Can you see that? If I took the sine squared theta from both sides, I'd have the cosine squared theta equals 1 minus sine squared theta. Okay? You need to recognize those rearrangements of the common trig functions, identities, I should say. Very, very important. Familiarity of your math is what will get you a high score on the AP exam, right? The things that we expect you to be familiar with are what give you the insights into simplification. Okay? So, I mean, I could go crazy with this, right? So let's do two things. Let's do one thing where I go crazy with it. Okay? So, if I did the derivative of this, I could say the derivative of cosine is what? Negative sine, very good, of y dy dx equals, oh crap, how am I going to do that? How am I going to do that? Well, I could write this as 1 minus the sine squared y to the 1/2. Do you remember that? What's under here is raised to a power of 1. This is the square root. It's power over root. You should be able to go back and forth between fractional exponents and radicals. That should be something you can do, like, you know, saying your phone number. Okay? Let's find a second order implicit derivative. I do higher order derivatives, but I'm going to do one on here because this is implicit and it should go together. So let's check out something like this. X squared plus y squared equals 25. What kind of shape is that? You should know. HK is 0, 0. So that's x squared plus y squared equals r squared. It's a circle with a center at 0, 0 and a radius of 5. Okay? And I'm going to ask you now not to just find dy dx, but I'm asking you to find d2y dx2. All right? And that looks a little bit horrible the way that 2 is showing up here, so let me rewrite that. Find the second derivative with respect to x of that function. The second derivative means I take the derivative twice. So you can imagine the third derivative means I take it 3 times and the fourth. At some point it becomes useless to do that, except in very rare occasions like L'Hopital. But the first, second, and third derivatives, they have regular applications that stretch into physics and graphing. So we look at 3 in general. I'm only going to look at second derivative because it's just an iteration of it to get the third derivative. So let's do this. Let's do the derivative. Right. So the first derivative, that's what I'm going to do. So this would be derivative 1, okay? 2x to the 1 dx dx plus 2y to the 1 dy dx equals 25 is 0 dx dx, yes? Okay? Now, this is very, very important. You need to know. I don't just want, I need to know what dy dx is. Okay? So I know that I'm going to move my 2x over, negative 2x. I'm going to divide by what's in front of that, positive 2y, and that's going to be dy dx. Right? That's because you've done enough of them, and I don't want to, we're over 30 minutes and I want to get this done. But what did I do? I moved this over, then I divided both sides by 2y, and now that's going to simplify, right? That's going to simplify to negative x over y, which you should have known. Remember I said it's every circle at 0, 0? We found that out already. That's just proving it. Okay, that's negative. That is dy dx. If I asked you to find dy dx, you'd be done. But I didn't ask you to find dy dx. Okay, so let's look at this now. We've got the first, and let's look at the second. To do the second, I could do the second here implicitly, and I'd get a lot of messed up terms, but this is already simplified really nicely, so let's just take the second of that expression. That's not the only reason I needed it, but it's a good place to start since it's already solved for dy dx. So what I'm saying is I want to take the derivative with respect to x of this expression dy dx equals negative x over y. Well, when I take the derivative of that, basically the derivative of the derivative becomes the second derivative with respect to x, which is what I wanted to solve for. And on the what this boils down to, this becomes negative. I'll leave the negative out in front. The negative quotient rule. That's what it is. It's this function divided by that function. So I've got to do the derivative of the top is 1 dx dx, I don't need anything else, times y, minus the derivative of the bottom, which is dy dx. Well, y to the 1 becomes 1, y to the 0, or 1 dy dx, 1 dy dx, all right, all times the top, which is x, all over the bottom squared, y squared. Okay? So hopefully you can kind of see how that works. Now I have this, I simplify that down, and I'm all good to go. But before I simplify that down, I immediately look and say, look, I know what dy dx is. dy dx is the expression negative x over y. This is why I needed that. I needed that so I could do a substitution. And if I did a third derivative, then I'd use this to substitute in. You see what I'm saying? That to substitute in, and I could find as many derivatives as I would want in that ever-expanding chain of derivation. So let's simplify this thing down. This, of course, let's scroll up a little bit here. This, of course, becomes y minus negative 1 over y times x over y squared. Well, this is obviously negative x over y. That's what that becomes, right? Oh, I take that back. Because I scrolled up, I couldn't see it, and this board is killing me. That should have been negative x over y, right? So this should have been negative x over y. So that would be negative x squared over y. My bad. So I inserted negative x over y because that's what dy dx was worth. And then I multiplied it by x and got negative x squared. So I've got this really crazy fraction, right? I've got, let's do this, y over 1, okay? And what's the opposite of negative? It's positive. X squared over y, all over y squared. So I'm going to go ahead and say, let's make that over 1 as well. Why did I do that? Why did I make all those things over 1 when I had fractions in part of it? I want fractions in all of it. Now I've got a compound fraction where I'm going to need to get a common denominator on top and simplify the top. Then I can invert and multiply to finalize my answer. So since the common denominator between 1 and y is going to be y, I have to just multiply this one, top and bottom, by y. All right? So as we look at it now, continuing on, it's still the opposite of, right? I'm still working what's in there. The opposite of y squared plus x squared all over the common denominator y. divided by, right, y squared over 1. And what's going to happen is I'm going to invert this divided by that, and I'm going to have this times the reciprocal of that. Yes? So it's no longer there. And I can continue, and I will, equals the opposite of 1 times that is that, and y times y squared is y cubed, right? So what I have is this, and I'm going to use my little 3 dots. Therefore, d2y dx is. I'm going to just put the negative in front of that. I could distribute into that, or I could put negative that, right? The opposite. So I'm going to write negative. And I can put x squared plus y squared. It doesn't really matter. I'll leave it alone, just so it doesn't confuse you. And that is our answer. Okay? Higher order derivatives. That's something we're going to do. But I wanted you to see how to do a second implicit derivative, because every other derivative, I just take the derivative, take the derivative, take the derivative. It's not a big deal. But implicitly, I need this substitutionary principle to allow me to keep going to take higher order derivatives. All right? So this is a circle divided by a cubic function, and whatever the opposite of that is the shape we get. Interesting to think about. Plug it into Wolfram alpha, see what kind of shape you get. All right? And that shape represents the second derivative. Oh, let's not forget that that's the second derivative on bottom as well. I don't want to make that mistake. So that is the end of implicit differentiation. Thank you so much. There's going to be a few more that I'm going to add to this derivative section. I'm going to add special functions, I'm going to add trig functions, and I'm going to add higher order derivatives as 3 supplementary ones to these 6 video lessons, and you can look through those as well. Thank you.